All right, folks, so let's get started on this beautiful Friday. Beautiful day to talk about chemistry. So we left off talking about liquids and its connection to intermolecular forces. Chapter 10, we talked about gases. So gases, we have samples, particles, where they're far apart from one another. So typically we can ignore attractions except for real gases. And that occurs when we have lots of particles in a small space. That's when we consider real gases. So liquids, on the other hand, those particles are already in the condensed phase and they're very close together. So we need to think more critically about attractions. So in chapter 10, when we talked about attractions, which term was that, A or B within real gases? A, B, A, that's the A, attractions, yes, so that particles are attracted to one another. So the big idea here within liquids, attractions, again, very, very important, and the general trend of what we see with attractions between molecules is the more attractions molecules have or particles have to one another, we see a lot of different properties and differences in properties. And so what we see, all right, one of those trends that we see when we boil something, so let's think about this. When we boil something, we are going from the liquid phase, right? We're going from the liquid phase to the gas phase. So we're essentially changing the distance between particles. In the liquid phase, they're all really bunched up close together. But in the gas phase, they're infinitely far apart. So when we boil something, we break all of the intermolecular forces within your sample. And so with that in mind, if we have to break all of those particle attractions, what that kind of tells us is that there's more attractions, it's going to be harder to separate those molecules. So what we'll observe is a higher boiling point, a higher temperature boiling point, all right? So we're going to be talking about a lot of trends in this chapter, so always fall back to the idea of intermolecular forces means particle attractions. How difficult, if there's more attractions, it's more difficult to break those molecules apart or particles apart. So within this example, at room temperature and like normal pressures, we see chlorine gas, so a chlorine sample in the gas phase. Bromine, on the other hand, so like one element down in the same group, is a liquid. Iodine is a solid. So let's think about this really critically here. If based on those observations, right, that chlorine is a gas, bromine is a liquid, iodine is a solid, which substance has the highest boiling point temperature, just based upon those observations? Can we think about which substance, chlorine, bromine, iodine, has the highest temperature boiling point? Iodine, yes, so I too, yes. Do we see that? Because it's a solid, right? So if iodine's a solid, so if you didn't get that, I want us to work through it. If iodine's a solid, are we, at room temperature, are we above or below the boiling point? We're definitely below. We're actually below the melting point as well, because, it goes solid, liquid, gas. And then the idea with chlorine, on the other hand, chlorine, it's already a gas. So that means at room temperature, we are already above the boiling point temperature. So do you see that? All right, so the answer here, which one has the highest boiling point temperature? It'll be I2. And so therefore, if iodine has the highest boiling point temperature, which sample is the most difficult? Which sample takes the most energy to turn into a gas? Which sample? Iodine again. And it all has to do with the idea of particle attractions. When we boil something, we are breaking all intermolecular forces. But if we think about iodine, right, I write I2, but really if we drew out the Lewis structure, it would look something like this. When we boil something, we are not breaking that covalent bond between iodine or iodine atoms, all right, that we're only changing the distance between the different molecules themselves. We are not breaking covalent bonds. I just wrote that, not covalent bonds. We're only breaking intermolecular forces. That's the big idea with these phase changes, because we don't want to change the identity of the thing. All right, and so from there, since we know iodine has the highest boiling point temperature, which sample between chlorine, bromine, and iodine has the most particle attractions? Iodine. So that's the trend here, that basically what we see as IMFs increase, we see a boiling point temperature increase. Okay, that's the big idea here. Yeah. That is based upon colligative properties. So this idea of intermolecular forces works really well with pure samples, right, where we only have pure I2, there's nothing else in there. So when you sprinkle in salt into water, yes, it lowers the lowers the freezing point. All right, and it has to do with the idea of vapor pressure, and you will learn more about that in Chem 1220 when you talk about colligative properties and you dive deeper into solution chemistry, okay? All right, yeah, so things get weird when you don't have pure samples anymore. Yeah. All right, so there we go. So the big trend that we will constantly fall back on as IMFs increase, boiling point increases. Okay, so into the idea of details of intermolecular forces. Just think of it as particle attractions. We talked about it a little bit in chapter 10, where we talked about the A and B terms. B referred to size of your particle, A referred to attractions. And we said generally as B increases, as size increases, A increases. And this actually has to do a little bit about one of the 5 intermolecular forces we'll talk about, but I just want to kind of show you maybe an anomaly here that shows us the power of what particle attractions can do and change in a sample. So here's that same list from chapter 10, and we said before, as B increased, we typically saw an increase in A. So if we plotted these points against each other on a scatter plot, that's what I have here. So what you see here is the B terms, the A terms, and that's kind of what you see. We see a straight linear line as B increases, A increases, right, for most of them. But there's one particle here that doesn't fit on the line. Do we see what that is? It's water. So do you see here water is kind of off the line? Do we see that? So the y-axis here is B, remember that's size, and A is attractions, particle attractions. So what this means is that water, H2O, it's relatively small, right? Its molar mass is only like 18 grams per mole. So it's relatively small, but it has a lot more attractions than like what fits on that line. Does that make sense? Right? Because it has more attractions because it's kind of offset from that line, just more so than just based upon its size in general. And this kind of gives us a glimpse into the ideas of what intermolecular forces, all of them that we need to consider. It's not just based upon size. So this is kind of like a glimpse of, you know, why is water over here? And I guess to spoil the story, it's hydrogen bonding. Hydrogen bonding is a very, very strong intermolecular force. It's the force that holds all of like our DNA and all the proteins and stuff inside our bodies. But I don't care so much about that. I'm not a biologist. Anyway, okay, so keep talking about attractions. And I told you way back in like chapter 1, chapter like 5, when we talked about thermochemistry, that the ideas of kinetic energy and potential energy would come back and haunt you, and that we have to keep thinking about this potential energy graph and the whole idea, the closer you bring two oppositely charged particles together, the more negative, the more stable your potential energy goes. That's this whole idea, you know, Q1, Q2 over D, that whole thing. That equation solves, like, that's like half of this class, is that equation right there. The idea of potential energy and attraction. So the idea of intermolecular forces isn't anything different. They're just electrostatic attractions between oppositely charged particles. The cool thing about intermolecular forces, they can be between full-blown charges, okay, like a full +1, -1, or a +2, -1, whatever, or they can be in attractions between partial charges. All right, and that gives us one of our other intermolecular forces we see too. So that's what I have here in parentheses. You can have attractions between partial charges as well, and we denote, remember, partial charges with these delta signs, and they are present in molecules that have polar covalent bonds. All right, okay, so that whole idea that we have attractions when we bring oppositely charged things together. So that's no new news to us. We'll just look into the details. All right, so these attractions that we see between different molecules, they are not as strong as covalent bonds. but they are strong enough to change a lot of the observable properties that we see. So like boiling point, melting point, vapor pressures, and viscosities, all based upon the idea that particles are attracted to one another. And I think if we think about this on a particulate view, we can very much predict the properties that are to come. But within this course, we'll talk about intermolecular forces and the details. Can we identify based upon a sample given what intermolecular forces are at play and what dictates the properties we see. All right, so here's an example, HCl. There's an attraction between the partially positive of the hydrogen and partially negative of the chlorine, and so that small attraction between different molecules causes these different trends and properties we see. Like if we think about HCl as just, a molecule, HCl, right? Hydrochloric acid. Just one HCl molecule is neutral, right? It's neutral. So this interaction that I'm depicting right here are two what we say are neutral molecules, but because there are permanent dipoles present, because we know HCl is a polar covalent bond, that idea of a permanent dipole, they can interact with one another, right? These dipoles interact with one another like little magnets, and that's why they're attracted to one another. Yeah. Yes, but not quite. Yes, but not quite. So let's keep going. All right. So here are the four main intermolecular forces, and I've listed them in order of increasing strength. All right. So just write those down. Okay. There's four of them. The first three are the most important when looking at how do I want to say this, like covalent molecules. And the last one is kind of a special case when we start mixing things in water, right? And I'll show you the examples and what criteria to look for all of these. So the first one is dispersion or London dispersion forces. I write this a billion times, but basically all of these different four intermolecular forces have their own trends. And so for the first one, dispersion, it's the weakest, all right? So I write here that it's the weakest, because it's written first, all right? It's the weakest, and typically what we see here within dispersion is that as the size or the weight of your molecule increases, London dispersion forces increase. And what we also see as surface area increases as well, London dispersion will also increase. The next one is dipole-dipole. What you want to look for within that intermolecular force, and oftentimes I call it IMF if you haven't noticed. You want to look for permanent dipoles. All right, permanent dipoles, or you can just think of any polar molecule. A polar molecule will have a permanent dipole. So, that might require you to, in your head, draw the Lewis structure, predict the electron molecular geometry, do the babies and bodybuilders thing in your head, and then predict whether that molecule is polar or not. So that's what you look for dipole-dipole. Then the last one here within molecules is hydrogen bonding, and what you are looking for are very electropositive hydrogens. It has a special criteria. Really, hydrogen bonding is a special case of dipole-dipole, but I'll show you those details. And this last one, 4, is a special case. It's really only important in solution chemistry, aqueous chemistry, when we dissolve stuff in water, ion dipole attraction. So just from breaking apart the word, it means we have a full-blown charge, an ion, so like a plus, like a sodium plus, or like a minus, like chloride minus, interacting with a dipole, such as water. Water is the universal solvent because it's polar, but really water is only good at dissolving other polar things. So the whole idea of in biology, they teach you like dissolves like. That's kind of like an oversimplification of solubility. Really, the real true rule of solubility when it comes to living beings or whatever, as living beings, we are mostly composed of water. So when there are very strong intermolecular forces between the solvent and the solute, your thing will dissolve. All right, so that's the whole idea of like dissolves like. If we have a polar molecule like water, it will dissolve other polar things as well. But if you have something really sticky on your hands, typically water isn't very good to wash that off. If you talk to your like older parents or grandparents, they might tell you that they used to wash their hands with gasoline all the time. Yeah, you look really surprised. I'm sure people in this room have done it, or someone's told you, oh yeah, just wash your hands with gasoline. Yeah, they totally did that because gasoline is made of hydrocarbons. It's non-polar, so you can like wash, your greasy hands very quickly with gasoline. Don't use gasoline, but we're using the different properties here. There's different intermolecular forces happening, causing for different types of solubility there. So that's my riff on biologists. Okay, all right, so let's go into detail of all of these. So the first one, the weakest one, is London dispersion forces. I already said the trend here. The attraction under the umbrella of London dispersion forces as molar mass increases or surface area increases of your substance, typically your London dispersion attraction increases as well. You need to see like a big increase in molar mass, not just like tiny like fractions of a gram per mole. I'm talking like big jumps. You'll see trends there. All right. And so the tip is here is that non-polar compounds will only have London dispersion forces present. If you have a nonpolar compound, it will not have any of the other four or three or four IMFs present. So that's kind of nice. When you have nonpolar things, you just consider London dispersion. So where does this come from? All right. So the whole idea of London dispersion, and oh no, my thing is dead. Is it dead? Yep, you're dead. The whole idea with London dispersion, and it's important in nonpolar compounds because where this attraction comes from, because it's weird, we're thinking about atoms, all right? They're just, Dalton thought of them as billiard balls. How are they attracted towards one another? And it's the whole idea that electrons are moving around your atoms fairly quickly, right? They're in this probability cloud around your nucleus. And so that whole idea that electrons around atoms move around tells us that, in a certain instance of time, if like in this example, we're looking at a helium atom, there's 2 electrons on that helium atom. Maybe in an instance of time that 2 of those electrons are on, let's say, one side of the helium atom at the same time. Just like for a fraction of a second, all right? Can you believe me for a second that they're both on one side at one time? All right, so if that happens, if both of those electrons are on one side of the helium atom at the same time, that for just a split second in time makes one side of that helium atom partially negative and then the other side partially positive, all right? So that's what we call a temporary dipole. This only happens, and it happens more often if your molecule has a ton of electrons. If there's a lot of electrons there already, then just by probability, you're much more likely to have an instance of time where, let's say, there are more electrons on one side of the molecule than the other. So that's that whole idea. So what's cool here is once you induce, we call this a temporary dipole, is once you have a temporary dipole, and you bring another molecule or atom nearby, if this side of the molecule is partially negative, then wouldn't these two, or the nucleus, be slightly attracted to that negative part of the neighboring atom? All right, so what this is called is we induce a dipole in another atom or a nearby atom, and that's what we see here. All right, so on this atom over here, it was partially negative at one point, and so in doing that, we kind of disrupt or induce another dipole in a neighboring atom. All right, and so there's an attraction, right? So what right there, that is depicting an attraction. Right. This is a very, very weak attraction, but it's still strong enough for us to explain a lot of different things. When we looked at the chlorine, bromine, iodine example, that is showcasing the power of London dispersion forces. That iodine, all those molecules, Cl2, Br2, I2, they're all nonpolar, but I2 is so much heavier. All right, and so it can do this a lot more than, let's say, chlorine. All right, so that's what it is. That's the whole source of London dispersion forces. The whole idea is temporary dipoles. These are non-polar molecules, but if we were to track all those electrons, but we know that that's impossible to do, right? But let's just say for a second, half of the electrons or more than half of the electrons are on one side of the molecule for a split second. That induces other dipoles in neighboring molecules. Yeah. Yes. Yes, because if you have less electrons, just by statistics, there's just a less likely chance that you might have an uneven distribution of electron density in your molecule. Yeah, so this is seen, if you have more electrons to keep track of and do this, then you can have that unequalness there. So if there's just more electrons, or that's why the whole trend, as your molar mass increases, because if your weight increases, the number of electrons increases. So that's that whole idea. All right, so yeah, London dispersion present in all matter, whether polar or non-polar. So really, this whole idea of London dispersion, I showed you, we're creating temporary dipoles. Another kind of factor, it's based upon the polarizability of your atom or of your molecule. So what that means, polarizability, it's just the ability to disrupt or distort your electron cloud. And it's the same idea here. If you can disrupt or distort that electron cloud easier, then you'll see more London dispersion forces. And so the trend here, polarizability, if that increases, London dispersion increases. Polarizability will increase with increased surface area and increased molar mass or weight of your molecule. So basically the trend here is LDF will increase when polarizability, polarizability increases, but also when surface area increases and molar mass increases. But I kind of just, I forget the middleman. I just say, okay, if LDF increases, when molar mass increases or surface area increases. All right, and so here's the example of surface area. All right, usually you want to look at molar mass first. So here's an example, all right, of two molecules. Okay, this is N-pentane and neopentane. All right, and so let's compare their intermolecular forces. So let's look at the boiling points first. So based upon these boiling points, which molecule has more intermolecular forces present in the sample, just based upon the boiling point? Do you remember the trend? IMF increases, boiling point increases. Yeah, remember, IMF just means attractions. So if molecules are more attracted to each other, it's harder to boil. It's harder to boil, all right? Because you have to rip all those intermolecular forces apart. So just based upon those boiling points, which molecule has more intermolecular forces? Which one? N-pentane. All right, because the other one's neopentane. So they're both called pentane. They just have different names. Yeah, so this one, N-pentane, has more IMFs. So if we look at the just individual molecule there, see how N-pentane is flat. Right, they're like little worms or little ropes, and they're flat, laying next to one another. So there's a lot more surface area and interaction between electrons to induce dipoles with one another. Versus if so, see how neopentane, it's the same molar mass. They're actually isomers of one another. See how they're both C5H12. You see that? So they have the same molar mass, but they differ in terms of surface area. So neopentane, it's much more spherical and compact, so it has less surface area, so there's less London dispersion there. So that's why N-pentane has the higher boiling point, even though these two molecules weigh the exact same. All right, N-pentane has the higher boiling point. All right, let's keep going. All right, so size, we kind of mentioned this before with molar mass. The larger the molecule, the more electrons, so the more this whole temporary dipole business can happen. And so the trend here, and we already mentioned it, as intermolecular forces increase, boiling point increases. So you see here with, if we look at the noble gases, so we go down the noble gases, neon has a boiling point of 27 Kelvin, dang, that's cold. Argon 87, krypton 121, xenon 166. So you can see boiling points are increasing, and also molar masses are increasing. All right, not so much of a difference in surface area. Molar mass can tell us the trend right there perfectly. All right, yeah, and so the reason we're just looking at London dispersion because all of these substances are nonpolar. So we can do that. Let's look at the halogen series. So there's diatomic fluorine. Its boiling point is 85. Diatomic chlorine 269, bromine 332, and iodine is 458. So we kind of already said, you know, like room temperature is like around here-ish, all right? So this is why chlorine is a gas, bromine is a liquid, and iodine is a solid at room temperature, all right? And it has to do with this, you know, incremental increasing of intermolecular forces as we go down a group because your atoms are getting so much heavier. What we see is increase in London dispersion, more molecule or atom attractions. It's harder to separate them. We see an increased boiling point within there. So that's what we see. Yes. Okay, so let's keep going. Oh, I already did this one. Shape. I already did the shape one, right? Yeah. So neopentane has the smaller, it's more compact, less surface area, so less intermolecular forces, a lower boiling point there. All right. So there we go. So I already did that one. Okay, so size and shape for London dispersion is most important in nonpolar substances. Okay, so let's look at these substances, all right? I give you a bunch of information, molecular weights, dipole moments, boiling points of different substances. So let's rank these molecules, all right? Rank them in terms of their intermolecular forces just based upon their boiling points. So which of these has the least amount of intermolecular forces present? Propane. So if I'm talking about low intermolecular forces, that means low boiling point. So we want to look for the lowest boiling point substance. So in this example, the series, propane has the lowest IMF, and then acetonitrile would have the highest, right? Highest, right? So let's see with what we know so far, does this match the trend that we know? We know that as IMF increases, that boiling point should increase. It's a really great indication of attractions there. So we did that. So does London dispersion fully explain this trend? So when we look at London dispersion, what factor are we looking at? Molar mass, pretty much. Molar mass or surface area if the molar masses are the same. But let's look at molar mass. So let's look at those. So propane is 44, and it's the lowest, okay. Ether is 46, okay, it's a little bit higher, boiling point goes up. Acetaldehyde, oh, the molecular weight went down, 44, weird. All right, and then acetonitrile, oh, wow, that's 41. It has the lowest molar mass, but it has the highest boiling point. So hopefully your eyebrow is raising and be like, what's going on? This is bringing us to the next, our next intermolecular force. So we can't consider molecular weight or molar mass only. It only works well for nonpolar molecules. So what we see here, I gave you dipole moments. Dipole moments, if there's a non-zero dipole moment, it means we have a polar molecule. So if you look here at the dipole moments of this series, acetonitrile has the highest dipole moment, the highest Debye value, meaning that we have charges that are separated the most in space and will respond the most when put into an electric field. So the answer is no. And so, but if we do look at dipole moment, it does kind of help us out with this trend. Actually, no, really, if we look at dipole moment, doesn't it follow? It looks like as dipole moment increases, boiling point increases. We see that? Yeah? Okay. And that's what goes into our second intermolecular force here is dipole-dipole interactions. So as dipole moment increase, we see IMF increase, therefore boiling point increases. Okay? All right, so, and that's essentially what dipole interactions are. Dipole-dipole interactions. So, okay, remember, London dispersion. we have attractions between temporary dipoles. They only exist in a blink of an eye. But dipole-dipole interactions are attractions between molecules that have permanent dipoles. So if something exists permanently, there will be overall much, much more attractions than something that only has temporary dipoles. All right, so that's why we say dipole-dipole interactions are much stronger. So the big idea here is you need to look for something, molecules individually having permanent dipole moments. So if we look at acetonitrile here, we have a nitrogen and like 2 carbons in a row. So what we see here is a overall dipole moment in one direction. We have just like little spinning magnets. So if we have a sample of acetonitrile, all those those plus minus ends, they're going to be attracted to one another. But this exists permanently because it's built into the molecule itself. All right, so we can see how that makes it stronger than London dispersion. Yeah. All right, so there we go. All right, but sometimes if the molecule is much, much, much heavier, all right, sometimes London dispersion does win. All right, but when we're talking about small molecules, what we're doing here is fine. That dipole-dipole will win out. So let's look at some examples. All right, so here I have 4 compounds. There are boiling points because remember, boiling points is a measure of just overall attractions. It doesn't tell us which one. It tells us kind of all of them at the same time. They're molar masses, so let's predict whether these are polar or non-polar. I hope we don't have to think about this too hard. Diatomic fluorine is non-polar, right? The same atom that just bonded together. Argon is nonpolar because it's just an atom. HCl, polar or nonpolar? Polar, yes. H2S, polar or nonpolar? Polar. In my mind, I think, oh, H2S looks like what? H2O, yeah, because sulfur is right under oxygen. It's bent, 2 lone pairs. Yeah, okay, so these 2 are polar. All right, and so let's look at those boiling points and molar masses. So if we look at those molar masses, like, they're not too different. To me, they're not very different. Like, you might say, no, Dr. N, argon's the highest. No, like in the grand scheme of things, argon only has like 4 more electrons than the lowest one. So within thinking, trying to apply the idea of London dispersion here won't work because the molar masses are really similar. They all have similar number of electrons. But if we look at the whole idea of polar versus non-polar, it works out better. It works out a lot better because what we see here are that the polar substances have higher temperature boiling points. Yes, they're in the negatives, but do note that these like HCl and H2S, the polar ones are at a higher temperature. You need to put in more energy to separate these little magnets, these little permanent dipoles from one another because they're constantly sticking to one another. And you need to give that sample way more energy to get it into the gas phase. All right, so we see that? So see polar, non-polar, polar molecules, much higher boiling points. Okay, great. Let's look at these 2 substances. Same idea, right? Acetone has a permanent dipole. Do you see it? I mean, I drew it for you, right? So you can see that the positive end is attracted to the negative end of your acetone. And then this molecule, which is called, do we know what that's called? 4 carbons? Butane, yes, butane. It goes meth, eth, prop, but. Okay, and then the next one's pent. Yes, okay. So that is butane, 4 carbons. That is a non-polar compound because carbon and like a carbon-carbon bond, that's delta E or delta En is 0. Carbon H bond is a delta N of En of like 0.4, which falls under non-polar covalent. So all hydrocarbons are non-polar. That's why our grandparents wash their hands with gasoline. All right. Okay. So do you see the idea of dipole-dipole attractions here too? Yeah. Acetone, polar, much higher boiling point. There we go. I think if you even compare the molar masses of, I think they both have like very similar molar masses, but because acetone is overall polar, it has, an overall dipole moment. They're like little magnets. It's harder to separate them, harder to boil, higher boiling point temperature. Yeah. Oh, N just means straight. Yeah, so there's like For example, rubbing alcohol is propanol, which is 3 carbons with an OH group, but really it's isopropanol. So these prefixes N versus iso and neo, it just tells you how do we distribute those like 3 or 4 carbons in space. Are they connected to one another, or do we put them in a line? You will get into that more in organic chemistry, where it matters. Because remember, composition and structure matters. Yes. And that's being shown here. Like both of these molecules, a lot of the other molecules, they were isomers of one another. Their compositions were exactly the same, but their structure is completely different. Therefore, we see different properties, such as boiling point. And it all has to do with intermolecular forces. Okay, so boiling point, we already said, is a really good indication of intermolecular forces. We said as your attractions increase, we usually see a boiling point temperature increase. Previously, we said that, as molecules or atoms got heavier, we usually saw increases in boiling point, increases of intermolecular force because of London dispersion and weights off of the periodic table. So if we look at this graph here, we can kind of see that on this. So ignore the left part for now. But if we look over here on the right part, we see as we go down a group, we see a successive increase of boiling point temperatures, just like we saw for chlorine, bromine, iodine. The boiling points as we went down increased because of London dispersion. And we see the same thing for the other parts of this graph as well. But what we haven't talked about yet is something that can explain, okay, what's going on right here. All right, actually, so within group 4, group 4A elements, if we attach them to hydrogen, if we go down the group, so like CH4, so that's group 4 attached to hydrogen, versus we go down to silicon, then germanium, and then tin. If we attach hydrogens to it, 4 of them, we see just an incremental increase in boiling point temperature. IMFs are increasing basically linearly here. We see increase in temperature. But do you see these guys? So these group 7A, 6A, and 5A substances, the lightest molecules of these groups are the ones with the highest boiling points. That's way, way weird. All right, so we need another factor here, another factor to kind of explain this. And this comes to our third intermolecular force, hydrogen bonding. Yeah, there it came to me. All right, and so the idea of hydrogen bonding will explain that weird, like, okay, why are the lightest ones have the most intermolecular forces? Then it goes down, and then it kind of increases linearly. So yeah, it's explained by hydrogen bonding. All right, so that is the drastic change that I'm talking about. All right, so hydrogen bonding. Basically, hydrogen bonding is a very special case of dipole-dipole interactions. It's still a dipole-dipole interaction. It just has a specific criteria. It has to be between a hydrogen that is very electropositive. All right, so if we look here on the right here, water is a great example of what can hydrogen bond. The hydrogen atom on water molecules, those hydrogens are made very, very electropositive because they are attached to a very, very electronegative oxygen atom. And so if you put another water molecule nearby, that oxygen is very, very electronegative. So what happens is that this particular interaction, all right, between the very electronegative oxygen and very electropositive hydrogen makes for a very, very strong dipole-dipole interaction. It's super strong. It's what holds together our DNA. It's what holds together the tertiary structure of our proteins. Super strong. All right, they build us. The idea of hydrogen bonding. So this particular interaction is very, very strong, all right? And the whole idea is that we have to make a very electropositive hydrogen. That's the thing in red right here. And it's made very electropositive because it's attached to a very electronegative atom like oxygen. But we also see it when we attach hydrogen to other electronegative atoms such as fluorine. And we also see it when we have a hydrogen attached to a very electronegative atom like nitrogen, all right? So we see hydrogen bonding when it is attached. Let me just go to the next slide, okay? These are the requirements for hydrogen bond. Not everything can hydrogen bond. Not anything with hydrogen can hydrogen bond, only very, very specific criteria. You need a covalent bond to hydrogen, all right? And that thing attached to hydrogen needs to be really electronegative. So only if it's attached to fluorine, nitrogen, or oxygen. And there has to be a lone pair on the fluorine, nitrogen, and oxygen, all right? So that's what I have here. What you want to look for are hydrogens attached to oxygen. There needs to be lone pairs. A hydrogen attached to a nitrogen, there needs to be a lone pair on that nitrogen. Or a hydrogen attached to a fluorine. Fluorine can only make one bond, so it's just HF. But you can have like alcohol groups or amine groups that can hydrogen bond, all right? So let me show you this molecule. So anything with that can hydrogen bond. If I remember the compound ammonium, do you remember what the formula for ammonium is? NH4, NH4 plus. Very good. All right, so if you draw the Lewis structure of NH4, let me do it over here. All right, it looks like this. Okay, can that hydrogen bond? It can? That can hydrogen bond? Oh, yeah, Dr. N, there's a nitrogen attached to a hydrogen. You said nitrogen, hydrogen. But I also said what has to be on that nitrogen? A lone pair. Is there a lone pair on that nitrogen? No. So tertiary amines, when you go to like biology and stuff, can't hydrogen bond. They can do other intermolecular forces, but they cannot hydrogen bond. But if I drew ammonia, so NH3, if I drew NH3, that, yes, can hydrogen bond because it looks like this with a lone pair on it. Okay? But ammonium cannot hydrogen bond. Okay, that was a trick question. No. All right, yeah, stuff about DNA. Okay, so let's look at these two isomers. They have very similar formula weights. I think they're isomers of each other. All right, so they have the exact same molecular formula, but they have way different boiling points. So let's look at this. A boiling point of one propanol is 97 degrees Celsius. Boiling point of ether is 8 degrees Celsius. So of these, which one has more attractions overall? Which one has more attractions? Based upon the boiling points. Don't even look at the molecule. The propanol, yes, has way more intermolecular forces. So let's compare all of the intermolecular forces present in this sample and see if we can't arrive at understanding the boiling point that we observe. So the first one we always look at is LDF. Do both of them have LDF? Yes, and they're actually the same because they're the same molar mass. All right, they're the same for both because they have the same molar mass. All right. The next one is dipole-dipole, right? Do both of them exhibit dipole-dipole? Yes, they're both polar. Yeah, there's oxygens. Basically, if there's like weird functional groups on things, like for organic molecules, if there's a functional group on there, so like an alcohol or an ether group, it is a polar. Yeah, so both are polar. All right, both are polar. But why are their boiling points so different? Because one can hydrogen bond, but the other can't. So which molecule can hydrogen bond? Only the propanol. So we see the ether example. Yes, there's a highly electronegative oxygen, but is there a hydrogen directly attached to it? No, only carbon. So our ether here cannot hydrogen bond. All right, so only our propanol example can hydrogen bond. So only propanol. All right. So does that the comparison we made here? So that means that propanol has way more intermolecular forces because it can hydrogen bond, and the ether can't. Does that agree with the boiling point that we see? Yes, it does. Higher boiling point, more IMFs. Propanol can hydrogen bond, so that's why we see it. Okay, there we go. All right. Oh, this is a tough one. All right, so I have a sample of water and hydrogen together. Water and hydrogen. So remember what water looks like. Water looks like this. There's lone pairs on it, right? Hydrogen just looks like that. If I have a mixture of those two substances together, like you see here, which of these pictures depicts the hydrogen bond interactions. So remember, hydrogen bond, it's just a special dipole-dipole between the electropositive hydrogen and another electronegative atom. So of which of these pictures depict the hydrogen bonding? The hydrogen bonding. Discuss it with someone near you. This one's tough. I'll give that to you. Which one depicts red lines that are only indicating hydrogen bonds? Okay. All right, I want to go through these. Does anyone think it's B? Okay. Let's look at B. So B is circling the line between an oxygen and a hydrogen. So that line represents what? A covalent bond. Is a covalent bond an intermolecular force? Intermolecular is between two different molecules. We circled a bond inside a molecule, so no, B cannot be the right answer. B is just circling a covalent bond, and that is not intermolecular forces. Okay, we have to draw interactions that are between different molecules. Okay, let's look at A, because that's the other one that's wrong. Who thought it was A? This one's hard, okay? Because A, look, there's a bunch of lines between hydrogens and oxygens. But you need to look at between which hydrogens and oxygens. So let's focus in on one of these, all right? I'm gonna look at this interaction right there, all right? Yeah, there's a hydrogen and an oxygen, but what is that hydrogen attached to? Just another hydrogen. So is that an electropositive hydrogen? No, it's just a normal hydrogen, all right? So it's not highly electropositive. We need interactions between hydrogens that are on water and oxygens that are on water. So they can't be between the neutral hydrogen molecules. So this one is incorrect. Are there any hydrogen bonds being depicted? So this one, this bond right here, okay, my pen's dead again. Come on. This bond right here, right there, is a hydrogen bond. I can't go through all of them, but like some of them are not hydrogen bonds. You see that? Okay, all right. See, that's tricky. That's tricky. All right, so C is the right answer. There's less being drawn, but all of them are hydrogen bonds, right? They're all hydrogen bonds. They're all between electropositive hydrogens and electronegative oxygens. So none of them are between the neutral, like H2 molecules themselves. Tricky. All right, feel good about hydrogen bonds? Okay, what's the rule? Hydrogen attached to oxygen, nitrogen, or fluorine, but there needs to be a lone pair, at least one lone pair. Okay, yes, that's what it is. All right, the last one, ion-dipole interactions. Again, I mentioned really important for solution chemistry, so when we dissolve stuff in water, this is why we can dissolve salt in water. Remember when we talked about NaCl solid, ionic solids, lattice energy. Does that ring a bell? Lattice energy. Tons of energy we get back when we form ionic bonds. So those bonds are really, really strong because they're full-blown charges attracted to one another. But the cool thing is when you put salt in water, your cations and anions break apart. They break apart because the interactions between polar water molecules and the individual ions are actually really, really strong. So what's being depicted right here are the individual ions here, chloride and sodium interacting with water. The slightly negative part, so like the slightly positive part, the two hydrogens, all right, on water are interacting with the negatively charged chloride, solvating it. If we look at sodium, the negative but part of our water molecule is attracted to that positive sodium, solvating it. So this interaction is very, very strong. So when we say, so remember in chapter, I don't remember, 4, when we said sodium chloride aqueous, we said that actually means, because sodium chloride is a strong electrolyte, sodium chloride aqueous actually means sodium plus aqueous, chloride minus aqueous. So when we said this previously in chapter 4, what we were actually talking about was this attraction, ionic ion dipole attractions between the water molecules themselves, all right? And so the reason stuff dissolves is the idea of, okay, is this attraction, this ion dipole attraction, is it stronger than the lattice energy? All right, so I'm bringing back chapter 8 stuff, all right? So let's look at, and chapter 4. Okay, remember the solubility table, right? Remember it? Well, maybe not, because you didn't have to memorize it, you just had to learn how to use it, right? So if we look here, the things that were really insoluble, bottom of the table, things that were really soluble, top of the table, like sodium, anything attached to sodium or nitrate was really, really, really soluble. All right, so let's kind of walk through this. Based upon this table, which of these compounds, these 3, has the poorest solubility? Poorest solubility. The iron one. The iron one has poor solubility, right? Because sulfide is under insoluble ionic compound, right? So that means if we put iron sulfide in water, is it going to make iron sulfide aqueous? No, it's going to stay a solid. So will it make ionic attractions? No, because it's not making anything that's aqueous. But let's go deeper, okay? Because you guys know this, all right? Let's go back to chapter 8. Of these compounds, which one has the largest lattice energy? Iron sulfide. It's the hardest one to break apart, right? If we do the Q1, Q2 stuff, all right, calcium is +2 and chloride's -2, iron is +2, -2, sodium nitrate is +1, -1. This is the one that has the largest lattice energy. So it's going to take the most energy to break apart into ions. Right? So what that's saying to us is that iron sulfide doesn't make very, very strong ion dipole interactions. That's why it doesn't split apart, that it would rather stay as a solid because of how strong that lattice energy is. See how it's all coming together? All right, that's how we read that. All right, yeah, so then let's think about it. Do very soluble ions like sodium, nitrate, stuff like that, do they make strong or weak ion dipole attractions with water? The question is for very soluble ions, so things that are in our soluble ionic table, do they make strong ion dipole attractions or weak ones? Yeah, if they break apart easy, what's breaking them apart? Water, because they're making new bonds in the form of ion dipoles. So they're making strong ion dipole interactions because the newly formed bond has to be stronger than that of the lattice energy. Okay, so strong. Right, has to be strong. So in this case, iron sulfide, it makes weak ion dipole because it's not very soluble. That makes sense? The new bond we form very strong. All right, so let's keep going. All right, so here's the summary of everything, basically. All right, London dispersion forces. Everything has London dispersion forces, all right? Important in what type of compounds? Do you remember? Non-polar compounds, non-polar, right? Because non-polars won't have anything else. And the trend here is your London dispersion force will increase when molar mass increases or when surface area increases, all right? All right, dipole-dipole forces. The requirement, you need a polar molecule, meaning that you have a permanent dipole present. And so really the trend is here, essentially the more polar your molecule, the more IMF. So what you'll see is that your dipole-dipole will increase as your overall dipole moment increases. But oftentimes we're looking at things are they polar or not polar? That's usually what we're doing because we have to kind of give you what a dipole moment is, all right? All right, so hydrogen bonding. We need hydrogen attached to either an oxygen with a lone pair, nitrogen with a lone pair, or fluorine with a lone pair. Oops, I wrote nitrogen. Whoops, I wrote fluorine. Here we go. All right. The trend is here, I believe it's the higher the difference of electronegativity between the two atoms, the higher the hydrogen bonding interaction. So in this case, I think HF will have the highest, the most attraction there. All right, and then the last one here, ion dipole forces. We're not going to go into too much detail. Just know where that force comes from. We have ions dissolved in water. So in this chart, it's literally the same thing. I like this chart because it has energy values of how strong are these bonds that we're forming. All right, so we have 1 minute. So let's see if we can't predict the types of IMFs present in these samples. All right, water, does it has London dispersion? Yes, hopefully you don't think about that too long. Everything has dispersion. Does it have dipole-dipole? Yes, because it's polar. Does it have hydrogen bonding? Yes. Does it have ion dipole? No. Okay, CF4. CF4 is polar or nonpolar? Nonpolar, so it has dispersion. Does it have anything else? No. All right, we'll just stop there because it's 55. So we'll finish this on Monday.